Imagine your order service suddenly goes down. Customers are not able to check out. Alerts are firing everywhere, and you're sitting and going through the logs trying to understand what exactly broke. And what you find makes no sense at all. The order team did not deploy anything. The payment team also did not deploy anything. So then what brought down your order service? The user team simply renamed one column in a database. Sounds strange, na? One team is doing their own work, and a completely different team's service goes down. But see, this is exactly what happens when multiple microservices share the same database. This is not some rare accident. This is the normal result. So in this video, I will show you why companies like Amazon and Netflix never share databases, and instead, they follow one very foundational pattern called database per service. Let us go back to where almost every system starts. A simple e-commerce application built as a monolith. Suppose we have 5 modules inside it: user, order, payment, inventory, and shipping. And since it is a monolith, all 5 of them are talking to one single database. One single place which is holding the users, orders, payments, inventory, and shipments tables. And see, in the beginning, this is actually very nice. You need data from 2 tables? Just join them, simple. You need to update 3 things together? One transaction, finished. You want a revenue report? Everything is in one place only. So honestly, life is good. The monolith is not a bad choice at all. For a small team, it is actually the correct choice. But then the company starts growing, and that is exactly when the problems start coming. Now see what changes here. Notice carefully. Nothing changes in the database itself. The organization changes. Now different teams are owning different modules. The user team owns the user part. The order team owns orders. The payment team owns payments. But underneath, all of them are still connected to the same database. And this one shared database is now going to create 3 very specific types of problems. First problem, tight coupling. Suppose the order service is reading directly from the user's table. It has written its logic based on the user team's schema. Now the user team renames a few columns. For them, it is a very small, harmless change. But suddenly the order service starts failing. A change done by one team has broken a completely different team's service. This only is called tight coupling. Second problem, database ownership. Who actually owns this database? Honestly speaking, nobody. Every team is modifying the tables. Every team is writing migrations. And when everybody owns it, then actually nobody is responsible for it. Third problem, deployment dependency. The order team is ready to ship, but the payment team is already doing some changes in the same database. So now the order team cannot move. They are blocked. The order service was supposed to be independent, but it cannot deploy without first coordinating with another team. And like this, you have lost one of the biggest reasons for which you came to microservices in the first place: independent deployment. So now, how do we solve all of this? The answer is surprisingly simple. The database per service pattern. The rule is just one line. Every microservice owns its own database. The user service gets its own database. The order service gets its own database. The payment service also gets its own. Each service becomes the only owner of its data. Only that service can create its tables, change its schema, run its migrations, and query its data. No other service can go inside and touch that database directly. And this one simple rule draws a clean, strong boundary around every service. Now the user team can rename as many columns as they want, and the order service will not even come to know. The coupling is finished. Now there is one rule which makes this whole pattern work, and I want you to remember it very properly. A microservice must never directly access another microservice's database. Let me say it once more, because this is the main point. A microservice must never directly access another microservice's database. So when the order service needs customer information, then what should it do? It should not go inside the user database. Instead, it should ask the user service through an API. The user service will query its own database and give back whatever is required. The data should come out only through the front door, which is the service's API. never through any backdoor database connection. This is the thing that keeps the ownership clean. And whenever you see one service reading directly from another service's tables, just understand, this is almost always an anti-pattern. This is the coupling trying to come back again. But wait, now one new problem has come. What if the order service needs customer information for every single order? Does it have to call the user service again and again every single time? Technically, yes. And that becomes a problem. Because every such call is a network hop. And network calls add latency. More latency means slower responses. At a small scale, it does not matter much. But at Amazon scale, with millions of orders, these small delays keep adding up. So we removed the database coupling, but in return, we got a communication problem. We did not remove the problem. We just shifted it from one place to another. The common solution for this is data duplication using events. Suppose a user updates their email. The moment this happens, the user service publishes an event. Let us call it user updated and broadcasts it out. Now any service which is interested can subscribe to it. The order service is listening, it hears user updated and quietly updates its own local copy of that user's information. So now, when the order service needs customer details, then what does it do? It simply reads it from its own database. No API call, no network hop. The data is right there, local and instant. This is called event-driven architecture, and it goes very well with database per service. But there is one trade-off. That copied data is not updated at the exact same moment when the original changes. So instead of strong consistency, you get eventual consistency. So now let us see everything that this pattern gives us. There are 4 big benefits. First, independent deployment. Teams can ship their services on their own time without any cross-team database coordination. Second, independent scaling. Suppose there is a flash sale. The order service is getting very heavy traffic. With separate databases, you can scale only the order service and leave everything else as it is. This saves real infrastructure cost. Third, technology freedom. Each team can choose the right tool for their work. The user service may use PostgreSQL. The order service may use MySQL. The payment service may use MongoDB. This freedom even has a name: polyglot persistence. And fourth, better ownership. Every service owns its own data. That is it. Responsibilities become very clear. There is never any confusion about which team controls which data. Now let us be honest. Because this pattern is not free, and its biggest cost is something that everybody underestimates: joins. In the monolith, joining the data was very easy. Orders and users were sitting in the same database, so you just joined them and moved ahead. But now, these two tables are living in two completely separate databases, which cannot even see each other. So that traditional join, the one you have used your whole career, is simply gone. This is why teams move towards alternatives. One is API composition, where an aggregator service calls multiple services and combines their responses. Another one is CQRS read models, where a separate database is built only for reporting, and it is fed using events. But in both the cases, the message is the same. You sacrifice the convenience of joins to get service independence. Let us connect all of this to a system that you use every single day: Amazon. The user service manages the profiles. The product service owns the catalog. The order service handles the orders. The payment service runs the transactions. And every single one of them owns its own database. They never touch each other's data directly. They communicate only through APIs and events. Exactly the rules which we just discussed. And this only is the real magic. This is the thing that allows thousands of Amazon engineers to work in parallel without coming in each other's way. The user team can redesign their full schema on any normal day, and the order team will not even come to know about it. So let us bring it all together. The database per service pattern says only one thing: every microservice owns its own database. And this one single decision finishes tight coupling and unlocks independent deployments, independent scaling, and clear ownership. But understand one thing: it is a trade-off. Nothing comes for free. In return, You have to handle distributed transactions, duplicated data, eventual consistency, and the loss of that simple join. And here is the most important part. Database per service is the foundation, and it is almost always used along with some other patterns. The Saga pattern for transactions, CQRS and API composition for queries, and event-driven architecture to connect everything together. This is the reason why database per service is one of the most foundational patterns of modern microservices. If you get this one wrong, then nothing else will work properly. And if you're preparing for a system design interview, then you must definitely understand this one. Thank you for watching, and I will see you in the next one.